In the last video, you learned about derivation, how to find the derivative of a function, which is finding the gradient at any point on the curve. Now we're going to talk about the other half of calculus, which is integration. It is the exact opposite of derivation in the sense that addition is versus subtraction, or multiplication is versus division. With integration, you are finding the area under the graph to the x-axis. Why are we finding the area underneath the graph to the x-axis? Where is that coming from? I'll attempt to explain that to you. So let's say this graph is graphing the speed of a vehicle, and the car is going at 5 kilometers per hour constantly. And if I were to ask you, how far, what distance would the car cover after 10 hours? What would it be? It'll be 50 kilometers, right? 5 kilometers per hour for 10 hours is 50 kilometers. If we look at the graph, now that we know how to do it mathematically, can we do it graphically? If we take 10 hours and we find the area of this rectangle underneath the speed graph, 10 times 5, which is 50. If we find the area underneath the graph of the speed graph, we're going to find the total distance the car has traveled. Let's do another example. Let's say the car started at rest, and then it started moving and getting faster and faster as time goes on. Every hour that passes, the car moves 1 kilometer per hour faster. In this case, if I were to ask you, how far has the car traveled? It's difficult, right? Because it is speeding up. It's starting from a stopping position and it's speeding up. What you would probably do is just say that on the first hour, the car traveled 1 kilometer. On the second hour, it would have traveled 2 kilometers because it's going 2 kilometers per hour. And we'll just keep doing this until the 10th hour. And then we'll just add it all up together. For example, on the 10th hour, we'll say that the car traveled 10 kilometers. This one traveled 9, 8, etc. up until 1 kilometer. And if we add them all together, 10, 20, 30, 40, 55 kilometers. Now, this is not accurate at all because, as you can see, the rectangles are kind of sticking out. All these little triangles up here, they're sticking out there. And not only that, but there are triangles that are missing as well, right? So this is just an approximate. The other way we could have done this is to find the area. We already know that if we find the area underneath the speed graph, we're going to find the distance that it traveled. So it'll be a triangle, right? It's 10 down here and it's 10 up here, and the area of a triangle is half base times height. Therefore, it's half of 100, which is 50 kilometers. So this is distance. So that would give us the exact distance if we just find the area underneath the graph and the x-axis. Let's go now to another example. In this one, the car is starting at rest and then accelerating faster and faster as time goes on. It's now a curved function, no longer a straight line. The principle remains the same. If I were to ask you, oh, I won't do 10 hours this time, let's just do 5 hours this time. If I were to ask you how far this car has traveled in the first 5 hours, even if you want to find the area underneath this graph, it's going to be very hard because it is a curve. We could, of course, put in a rectangle at every point, like this, where we'll just get the area of each rectangle, add it all up, and we get an approximate distance. Now, this is not a very good estimation because, as you can see, the rectangles stick out quite a lot. We can, of course, instead of drawing a rectangle for every hour, we can do it for every, say, 2 hours, which will mean it's going to look like that, right? Now, this is going to be more accurate now to find the distance, but again, it's still not that great. And we can continue to do this until the rectangles get smaller and smaller and smaller until it kind of gives us a pretty good estimation, wouldn't you say? Just like in derivation where we want the distance between 2 points to get smaller and smaller, this is the same concept. We want the width of the rectangle to get so small that it may as well be 0, and it's going to give us a really, really good estimation of the area underneath the graph and the x-axis. And the word integration, when we add all of those areas up, all those areas of the rectangles up, we are integrating them. We're putting them all together, adding them up. That's where the word integration comes from. Let's go back to this graph for a second. If we plot the distance graph from this, we can find the primitive function. Let's do it together. Let's start from when time is 0. At 0, the car has not moved any distance. In 1 hour, the car has driven 5 kilometers. In 2 hours, it would have driven 10 kilometers. 3 hours, it would have been 15 kilometers. And I'm just going to stop there. Now you can see that this is a straight line graph. If we can find the function of this graph, if we can find the equation of this graph, then we can just find the total distance traveled for any time, correct? For example, if I say, how far has the car traveled in 4 hours? We can just follow this graph to the 4th hour and it'll tell us that it'll be 20. Some of you smart ones would have realized that in the last video, we went from this graph and deriving it to find this graph. In this video, we're going from this graph and we are integrating it to finding the primitive function. So the integral of the primitive function is the same thing. They're interchangeable, primitive or integral. If you have no idea what I'm talking about, I will show you here. It's fascinating, at least to me. Let's call this function dy dx, and it equals to 5. All right. Now we're trying to find the primitive function. To find the primitive function, we do the exact opposite of what we did for derivation. Therefore, to find y, we're going to, there is an x to the power of 0 here because, x to the power of 0 is 1. It's just 5 times 1. Now, when I'm going to plus the power by 1, now it's x to the power of 1, over or divide by the new power. So whereas before, we multiplied the power and then minus the power by 1, this time we're doing the opposite, backwards. We're plussing the power by 1 and then divide by the new power. There is an extra step in integration. There could have been a constant here because if you derive this, the constant would just disappear. So when you integrate, there could have been a constant there. So we got to be mindful of that. Therefore, the primitive function is 5x plus c. And if you have a look at this straight line, it really does look like a y equals 5x line, right? The gradient of this line would be 5 at any point. Therefore, this distance graph is the primitive function of this horizontal graph. This horizontal graph is the derived or derivative of the distance graph. So the distance graph if you derive it, it would become the speed graph. If you integrate the speed graph, you would get the distance graph. Does that make sense? I hope it does. Now let's learn about correct notation. You write integration like this. Y is equal to the integration of 5 in terms of x, right? And when you integrated it, it'll be 5x plus c. This is called indefinite integral. What's more likely is that you would be asked what is the distance traveled between, let's say, the first hour to the fourth hour. Whoop, like this. All right. And we can work that, because this is pretty easy. We can work it out now. It would be between 1 to 4 is 3. 3 times 5 is 15 kilometers. Okay. Or we can look at this, the distance graph, and we can say at the fourth hour it would have traveled 20 kilometers minus what's traveled on the first hour, which is 5. So 20 minus 5 is 15 kilometers. So we could have done that just by looking at the graph, but this is a pretty simple graph. Now, how would you do it with integrals? Well, you can do the definite integrals. We've just done the indefinite integral up here. Now we're going to do the definite integral, and it'll go like this. We're going to find the definite integral between 1 and 4 of the function of 5 dx in terms of x. And that's going to equal, and then we have this square brackets. When we integrate 5, we're going to get 5x between 1 and 4. Now this time, notice I didn't put in the constant. We don't have to worry about the constant for definite integrals, and I will show you why in a second. Okay, now we go 5 times the higher value, which is 4, minus 5 times the lower value, which is 1. And we're going to get 20 minus 5, which is 15. We're basically using the distance graph, which is what we did before, right? The car has traveled 20 kilometers when it hits 4 hours. We minus that first hour, so we can get what is traveled between the first and fourth hour. Okay, why don't we care about the constant in this case? Because even if there was a constant there, I mean, you could put plus c in here, but the plus c would cancel out anyway. So I guess it doesn't hurt, even if you did put it in. You're just making it harder for yourself, I guess. Now let's do a few more examples just to finish it off. Let's start with dy dx is equal to x squared. What would be its integral? We'll start with y is equal to the indefinite integral of x squared in terms of x. That's going to be plus the power by 1 divided by the new power plus a constant. All right, that's done. Next one, dy dx is equal to 4x to the power of 7. Again, y is equal to the integral of 4x to the power of 7 dx. Now we're going to add the power by 1, divide by the new power, plus a constant. That's going to equal to x to the power of 8 over 2 plus c. And then this one here, y will equal to, I'm going to skip drawing the integral sign because this is a bit long and I don't have room. I'm going to skip straight into the integration, which will be 2x cubed over 3 times 3. So we add the power by 1, then divide by the new power, which is 3. And the other term would be 6x to the power of 4 all over 7 times 4. That's going to give us 2x cubed over 9 minus, this one can be a 3, that one can be a 2, 3x to the power of 4 over 7. Oh, almost forgot, plus a constant. Don't forget the constant, because these are all indefinite integrals. Let's do it all again, but as definite integrals. Let's start on the left again. We're going to equal. Now we're going to start with a square bracket. The integral we put inside between 0 and 3. Then we're going to take the higher value, which will be 3 cubed over 3, minus the lower value. All right, that's going to give us 9 minus 0, which is 9. Okay, next one. We're going to start with the square bracket again. Write in the integral, minus 1 to 4. I'm going to spend an extra step. Words are hard. Extra step to simplify this. Like that. Then I'm going to substitute in. I'm going to start with the 4 because it's the higher value. Minus 1 to the power of 8 over 2. 32,768, which means it's going to be 32,767 and a half. And then this last one is the definite integral of this. Oh, I forgot the dx on these two. Oh no. Dx here, dx there. Let's start with the integration of what's inside. Minus 6x to the 4th, 7 times 4, between 1 and 2. Then I'm going to spend a step simplifying. 2x cubed on 9 minus 3x 4 over 14, I believe. 2. Then we're going to take the higher value, which is 2. So 2 cubed on 9. And this is still 2. So 3 to the power 4, 14. Minus, now we're on to the 1. 1 cubed on 9 minus 3, 1 to the 4, 14. I hope you're following. So this top bracket here is substituting in 2 for what's inside there, and then we minus the 1 for what's inside there. I'm not going to bother working this out because this is just putting it in the calculator and then finding out what it is. Of course, this isn't everything to do with integration. This is just getting your feet wet, just introducing you to the basics, just so that you're not as scared anymore, and I hope you can see how it works now. Let me know what video you want me to do next. Until then, study smart, not hard.